10.3 Comparison of Series. Let's explore two new tests for positive term series that will help us determine convergence or divergence. These two new tests will allow us to compare a complicated series that is similar to a simpler series. We will look at the direct comparison test and the limit comparison test. The direct comparison test exploration. Let a sub n equal 1 over 2 to the n and b sub n equal 1 over 2 to the n plus 1. Write out the first 5 terms of each series. So for the first one, when n equals 1, we get 1/2. When n equals 2, we get 1/4. n equals 3, we get 1/8. n equals 4, we get 1/16. n equals 5, we get 1/32. For the second one, for n equals 1, we get 1/3. For n equals 2, we get 1/5. For n equals 3, we get 1/9. For n equals 4, we get 1/17. And for n equals 5, we get 1/32 or 33rd. Notice that the bigger the denominator is, the smaller the number is. So when I compare 1/2 and 1/3, 3 is bigger in the denominator, so 1/3 is smaller than 1/2. 1/5 is smaller than 1/4. 1/9 is smaller than 1/8. 1/17 is smaller than 1/16. 1/33 is smaller than 1/32. So complete the statement. The series a sub n is greater than or equal to b sub n for all values of n greater than or equal to 1. Notice that a sub n is a geometric series. Find the sum. So our sum is going to be our first term, which is 1/2, over 1 minus r. And so basically you're multiplying by 1/2 every single time on that a sub n. So that's your r. And so this would give you 1/2 divided by 1/2, which is just 1. So that sum, and remember our sum was a over 1 minus r, is 1. Use your findings from question 3 and 4. What can you conclude about summation as n equals 1 to infinity of b sub n? We could conclude that that summation b sub n is less than 1, because every single value was less than the a sub n value, and a sub n sum was 1. So since each value is smaller, and each of the b sub n values is smaller, we can conclude that the summation of b sub n is less than 1. So now the direct comparison test. Suppose that the summation n equals 1 to infinity of a sub n and n equals 1 to infinity b sub n are series with positive terms. Let a sub n be greater than 0 but less than or equal to b sub n for all n. So if, and you can think of it as the largest one converges, then the one that, that they're comparing it to that is smaller converges. And this one, if the smaller one diverges, then the larger one diverges. So if you think the series converges, compare it to a converging series. The series you compare it to should be larger. So if you're thinking that the series you're looking at converges, compare it to something that's larger than it to see if it converges, okay? If you think the series diverges, so you're kind of thinking, okay, I think it diverges, then compare it to a diverging series, like the harmonic series is a diverging series that is compared all the time. The series you compare it to should be smaller than yours. And so those are the things you need to remember for that direct comparison test. So example number 1, determine whether the following series converge or diverge. And so the summation from n equals 1 to infinity of 7 over n to the 1/3 power. So I'm thinking that it might be divergent, okay? So if I think that it might be divergent, I would like to compare it to something that's smaller. And so if I compare it to 1 over cube root of n, that is smaller, because look, 7 on the top is always going to be greater than that 1 on the top. So if I compare it to 1 over cube root of n, for all n greater than 1, then I can look at, so for this, the summation n equals 1 to infinity of 1 over n to the 1/3. This is a p-series. And it diverges since p equals 1/3, and 1/3 is between 0 and 1. Diverges by the p-series test. Remember, if it equals 1 or if it's between 0 and 1, the p-series test says it diverges. Okay, so therefore, summation n equals 1 to infinity of 7 over cube root of n also diverges by the direct comparison test. Okay, and then part B, summation n equals 1 to infinity 2 to the n over 1 plus 3 to the n. So I'm wanting to compare this to 2/3 to the n. Okay, I know that this converges because this is geometric, and it has an r value that is between 0 and 1. Geometric that converges. And so now if it converges, then we said that the series you compare it to should be larger. Well, since this has a 1 plus in the denominator right here, that's going to make this always smaller. So 2 to the n over 1 plus 3 to the n is always going to be smaller than this 2/3 to the n. Okay? Put that like that. So therefore, this summation from n equals 1 to infinity of my 2/3 to the n converges because it is a geometric series with r equals 2/3, and 2/3 is between 0 and 1. And then, therefore, summation n equals 1 to infinity 2 to the n over 1 plus 3 to the n also converges by the direct comparison test. Okay, let's look at C. I'm going to change colors. Summation from n equals 1 to infinity of n minus 1 over n cubed plus 3. I would look at taking that and reducing it to 1 over n squared. And I would like to compare it to 1 over n squared. And then I had to start thinking about it. My n minus 1 over n cubed plus 3 is going to be less than 1 over n squared for all n greater than 1. And if you wanted to, you could look at your n equals 1 would be 0. N equals 2 would be 1 over 11. N equals 3 would be 2 over 30. N equals 4 would be 3 over 67. And then let's look at b sub n. N equals 1 would be 1. N equals 2 would be 1/4. N equals 3 would be 1/9. N equals 4 would be 1/16. So you can see that your a sub n is less than your b sub n for all n greater than or equal to 1. I don't know why I didn't put equal to there, but anyway. Okay. So since summation 1 over n squared converges by the p-series test, the summation n minus 1 over n cubed plus 3 also converges. Okay, and this one, if we take these, actually just the n squared divided by n cubed, it gives us 1 over n. So we're going to compare it to 1 over n. So our 8n squared plus 1 over 2n cubed minus 1 is going to be greater than 1 over n. For all n greater than or equal to 1. We know that this is the harmonic series that diverges, and it has to be less than the one you're comparing it to. So let's just make sure our a sub n, if I put a 1 in, I'm going to get 9 over 1. If I put a 2 in, I'm going to get 33 over 15. If I put a 3 in, I'm going to get 73 over 53, ... For b sub n, if I put a 1 in, I get 1. If I put a 2 in, I get 1/2. If I put a 3 in, I get 1/3. So b sub n is definitely less than 9, or 1 is less than 9. 33/15 and 1/2. 1/2 is less than 33/15, and so on and so forth. So since summation 1 over n diverges, summation 8n squared plus 1 over 2n cubed minus 1 also diverges. And can the direct comparison test fail? Well, let's look at that. Let a sub n equal 1 over 2 to the n minus 1 and b sub n equal 1 over 2 to the n. Write out the first 5 terms of each series. So for our a sub n, we would have 1, we would have 1/3, 1/7, 1/15, and 1/31. For our b sub n, we would have 1/2, 1/4, 1/8, 1/16, and 1/32. What do you notice about the terms of each series? Okay, well, your a sub n terms are larger than the b sub n terms. So, when we look at this, we know that b sub n converges. But remember what the rules said for convergence, that the series you're comparing it to must be larger. So this 1 over 2 to the n for this situation is not larger. So we're going to say just by looking at these partial sums, it is hard to tell. But the series you compare it to must be a larger convergent series or a smaller divergent series. This is a smaller convergent series. So it doesn't follow the rules for the direct comparison test. Okay, so now the limit comparison test. Suppose that summation n equals 1 to infinity a sub n and summation n equals 1 to infinity b sub n are series with positive terms. If the limit of a sub n divided by b sub n equals some L, where L is between 0 and infinity, then either both series converge or both series diverge. So this test is a great tool for comparing a messy algebraic series with a p-series. Just beware that you must choose a p-series with an nth term of the same magnitude as the messy series under consideration. For example, given the summation from n equals 1 to infinity of 1 over 3n squared minus 5n plus 7, choose the p-series summation n equals 1 to infinity of 1 over n squared. Note, you only need to consider the highest powers of n in the numerator and the denominator. So apply the limit comparison test to each of the series below. So what we would do for this one is we're going to let our summation b sub n be 1 over n cubed, okay? And by the way, our b sub n, this that we're comparing it to, converges, but b sub n is less than a sub n. So we can't use the direct comparison test. I just wanted to have you, think about that. So we're going to use the limit as n goes to infinity of our a sub n divided by our b sub n. It's a 3. And so to simplify that, we're going to multiply by the reciprocal of the denominator over itself. And limit as n goes to infinity. This is going to give us 2n cubed over n cubed plus 4. And now I can just focus on this, and this limit does equal 2. And since 2 is between 0 and infinity, by the limit comparison test, both series converge. Okay. And by the way, I hope you remembered that this was a p-series with p greater than 1. That's why it converged. Okay, let's look at the next one. Summation from n equals 1 to infinity of n to the 4th plus 5 over 4n to the 5th minus 2n to the 3rd plus 3. So we're going to take that n to the 4th divided by n to the 5th, and that's going to be our 1 over n, and that's what we want to make our b sub n. I'm going to change colors. And so we are going to compare to summation 1 over n, a divergent p-series, which is the harmonic. And so we're going to take the limit as n goes to infinity of our n to the 4th plus 5 over 4n to the 5th minus 2n cubed plus 3 divided by 1 over n. And of course, n over 1, n over 1. And this is going to give us n to the 5th plus 5n over 4n to the 5th minus 2n to the 3rd plus 3. And we're able to just look at the n to the 5th over 4n to the 5th. And that's going to equal 1/4 then. And since 1/4 is between 0 and infinity, by the limit comparison test, both series diverge. Remember, if you're comparing it to a divergent series, you're proving if you get a value between 0 and infinity, you're proving that they both diverge. If you're comparing it to a convergent and you get a number that's between 0 and infinity, you're proving that they both